Welcome back. This is Mr. Greenstein's geometry, and we're in probability 12.1 sample spaces and probability. Now let's try an experiment, a probability experiment, where a student guesses on 4 true or false questions. What is the probability that the student will make exactly 2 correct guesses out of the 4? So if we build a model, and this is typically what we'll do, just like that tree model we saw in the first video, we have the number of correct from 0 to 4 that could be possible, and let's list all the outcomes. Well, if you have 0 correct, there's only one way to get that, and that is to have all 4 questions answered incorrectly. And the same thing with the number of correct being 4. There's only one way to get that. All 4 have to be answered correctly. But if we want to get exactly 2, then we could say the first 2 are incorrect, whereas the third and the fourth are correct. We could say that the first and the third are incorrect. The first and the last are incorrect. The second and the third are incorrect. The second and the fourth, or the third and the fourth are incorrect. And those are all the possible different outcomes that could happen with exactly 2 correct. So what is the probability that the student will make exactly 2 correct guesses? Well, then we just look at the number of 1, 2, 3, 4, 5, 6. There are 6 exactly 2 correct. And the total number of outcomes in this whole thing is 16. So that means it's 6 out of 16, which can be reduced to 3 over 8. Or 3 chances out of 8, or 37.5%. The complement of an event is the probability of not having that event happening. So if we have an event A, then the probability of not A is the complement, and it's computed by 1 minus the probability that A will happen. So let's ask a question again. For example, we found the probability of getting exactly 2 correct answers was 37.5%. Now, the probability of getting exactly 0, 1, 3, or 4 correct, not exactly 2 that is going to be 1 minus the probability of getting exactly 2 correct. So that equals 0.625, or 62.5%. So you have a 62.5% chance of getting 0, 1, 3, or 4 correct, but not 2. Now let's take a look at the roll of 2 6-sided die, or dice. Solve for the following probabilities. We have the sum is not 6, and the sum is less than or equal to 9. So if the sum is not 6, first we look at the probability of getting 6. So the probability of getting 6 is equal to, well, if we look here, probability of getting 6 is in this area right here. So it's 1, 2, 3, 4, 5 out of all of these, which is 36. So it's 5 out of 36. The probability of not getting 6 then is going to be 1 minus 5 over 36, which is equal to 31/36. So that's how you compute A. Now let's look at the second one. The sum is less than or equal to 9. If we look at where that line goes, if the sum is less than or equal to 9, then that everything above this line is what we want to count. But there's a lot of things to count here. What if we count just these things and say not these things? So there's 1, 2, 3, 4, 5, 6. 6 things. So the probability that is greater than 9, which is the same thing as saying the probability of less than or equal to 9, but the not of that equals 6 over 36. And then we take that, the probability of greater than 9 is going to be, the probability that it is less than or equal to 9 is equal to 1 minus the probability that it will be greater than 9, which is 6 over 36. So that equals 30 over 36, or 5 out of 6. Geometric probability is the ratio of two lengths, areas, or volumes. And in this case, we have a target, and we want to see if we can hit inside the red bullseye. So we're going to calculate the probability of hitting in here. Now we're going to assume that no matter what I throw, it's always going to be within this circle, this big circle here, which is kind of a crazy assumption, but let's just pretend that this is the total area. So this is what we'll call our sample space. And if I calculate the probability of A, let's first measure the area of A. The area of A is the bullseye, so the area of A is going to be pi r squared, so that's going to be 9 pi. And the area of the total, which is the big round area here, that is going to equal, it's 9 radius, so 9 squared pi, or 81 pi. And if I want to find the probability of hitting in area A, which is the bullseye, that's going to equal 9 pi divided by 81 pi. And that is going to be 1 out of every 9 shots if I was to be completely random. The results of repeated trials are called experimental probability. So far we've been talking about theoretical probability. Let's actually look at some repeated trials. So a success is a favorable outcome. A failure is an unfavorable outcome. So the number of successes divided by the number of trials is the experimental probability. And sometimes we can actually experiment. Like on this color spinner, I'm going to spin it many, many times, actually 20 times. 5 times I get it red, 9 times it turns out green, 3 blue, and 3 yellow. So if I wanted to find the experimental probability that red will happen, it will be 5 out of 20, because I have 5 out of the 20 that I spun. The experimental probability of getting green is 9 out of 20. Experimental out of blue is 3 out of 20, and yellow is 3 out of 20. So theoretical probability is where you use deductive logic. Experimental probability is where you actually try it out in repeated trials. And we'll continue this conversation in the next class.